Hello everyone, welcome to a new lecture in the series of data-driven model predictive control. In this lecture, we will be discussing the recurrent neural network based nonlinear MPC, where we will first identify a recurrent neural network or RNN model using the input-output data, which is then used for solving the nonlinear MPC problem.
Here is the overview of the lecture. We will be starting with a brief introduction to neural network or NN, which is then followed by a discussion on recurrent neural network and a RNN based NMPC, and is followed by a numerical example. In general, a neural network can be considered as a data-driven model which is used for approximating nonlinear functions. Here we will be starting the discussion with a feed-forward neural network, which can be considered as a static input-output model. A feed-forward neural network is the most commonly used versions of neural network. And in this lecture, we will be denoting feed-forward neural network by NN. It is a nonlinear model and can be represented as in equation number 1, where x is the input vector containing all the input variables to the NN. Y hat is the predicted output, contains predictions of all the output variables. Fnn is the neural network function, which can be represented as a composite function as shown here. And here each of these individual components, F1, F2 till Fl, are the layers of the neural network and can be represented as in this figure 1. Here each layer will contain a finite number of neurons, where the neurons are represented using these circles. F0 denotes the input layer, which is simply passing this input, and it's not normally included in this model. F1 till Fl-1 are called as the hidden layers, and Fl is called as the output layer. And here this theta denotes all the parameters in the neural network, which consist of the weights and biases of all the layers in this network. Mathematically, this will be a nonlinear function, which is a mapping from Rn to Rm, where n is the number of input variables and m is the number of output variables. We can recall the definition of a composite function. In general, let f is a function from the set A to B and g is the function from set B to C. Then the composite function of f and g can be denoted by g composition of f, which is equal to g of f of x, and this will be a function from the set A to C. We have seen that the neural network has a composition of many layers, and each layer fi of the neural network can itself represented as a composite function as in equation number 3, where xi is the input to the layer, and ai xi plus bi is an affine function, and the sigma a is a nonlinear function. Each layer is a composition of this affine function and a nonlinear function denoted by sigma I, and this sigma I contains the activation functions for each neuron, where this activation function can be a nonlinear function such as tan hyperbolic, logistic function, etc. Here each layer will contain mi number of neurons, and this xi is the input to the layer. ai and bi are the weights and biases of the ith layer. The number of hidden layers plus output layer in the neural network we denoted by capital L, which we can also call as the depth of the neural network, and the maximum number of neurons in a layer denoted by width of the neural network. In order to understand the neural network in an in-depth way, we can consider an example. Here we will be using a particular activation function called rectified linear unit or ReLU. And for this ReLU function, if the input is negative, the output will be 0. And if the input is positive, the output will be same as the input. This can be graphically shown as in this figure, where the output is 0 for negative inputs and the output is same as the input for positive inputs. This will result in a piecewise linear function, which consists of two linear segments. This first one is a line segment with the slope 0, and the second portion is a line segment with slope 1. Now we will be considering different examples of simple neural networks with the ReLU activation function. First, we can consider the following functions, where we have a linear equation y equal to minus x minus 2, which will be a straight line with slope minus 1 and y-intercept minus 2, as shown in this figure A. And here we can see that the output of this function becomes 0 at x equal to minus 2. And for x less than minus 2, the output is positive, and for x greater than minus 2, the output is negative. Therefore, if you consider ReLU of minus x minus 2, for this portion, the output of ReLU will be 0, and for x less than minus 2, the output will be same as the input. Therefore, ReLU of minus x minus 2 will be a piecewise linear curve with one fold, where the line will fold at x equal to minus 2. Now let's consider another function y equal to 2x minus 4, which will be a straight line with slope 2 and intercept minus 4. And here we can see that the output of this function becomes 0 at x equal to 2. And for x greater than 2, the output is positive, and for x less than 2, the output is negative. Therefore, if we consider ReLU of 2x minus 4, output will be 0 for x less than 2, and the output will be equal to 2x minus 4 for x greater than 2. Here also we obtain a piecewise linear curve with one fold, where the line will fold at x equal to 2. Now let's consider another function y equal to 5x minus 15, which is a linear function with a slope 5 and intercept minus 15. And here we can see that 5x minus 15 will be equal to 0 at x equal to 3. Therefore, the output of this function becomes 0 at x equal to 3. And for x less than 3, the output is negative, and for x greater than 3, the output is positive. We have for ReLU of 5x minus 15, the output will become 0 for x less than 3, and the output becomes same as 5x minus 15 for x greater than 3. Now, in this figure A, B, C, we have considered these individual functions ReLU of minus 2, 2x minus 4, and 5x minus 15, where each of these functions has a fold at x equal to minus 2, x equal to plus 2, and x equal to plus 3. Now, if we consider a weighted sum of these functions as shown in equation D, we will obtain the plot as in figure D, where we obtained a piecewise linear curve with three folds. One is at x equal to minus 2, another one is at x equal to 2, and another one is at x equal to 3. Here, this curve has a positive slope, but after x equal to 3, we obtain a line segment with negative slope because we have included the coefficient as minus 0.6. And here we can see that if we adjust this coefficient, the slope of these curves can be adjusted. Also, we can see that the zero crossing of these individual components is dependent by this weight and this bias term. So if you adjust these terms, the zero crossing of these individual curves can be adjusted, which will also affect the shape of this final curve. Here, each of these individual components can be considered as a neuron in the network. And if we increase the number of neurons, we can introduce more number of folds in this line. Let's say if we have 100 neurons in this equation, we can have a piecewise linear curve with the maximum 100 number of folds. Each of these above function can be represented as a neural network with one hidden layer and a linear output layer. So here this A2 and B2 are the weight and biases for the output layer, and A1 and B1 are the weight and biases for the hidden layer, and sigma 1 is the activation function for the hidden layer. For example, if we consider this first equation, we have A2 will be equal to 1, sigma 1 will be equal to ReLU, A1 equal to minus 1, B1 equal to minus 2, and B2 equal to 0. Now, if we consider this last equation, we have A2 equal to a row vector which contains 1, 0.5, and minus 0.6. Sigma 1 will contain 3 ReLU functions. A1 will be a column vector which contains these weight elements minus 1, 2, and 5. And B1 will also be a column vector which contains these bias elements minus 2, minus 4, and minus 15. And B2 will be equal to 0. Another observation is that by adjusting these weights and biases, we can have different kind of shapes in the neural network. Now, when it comes to training, we will be doing the reverse step, which means we have to find the weights and biases so that the output of the neural network can approximate a desired curve or the training output curve. And as we observe here, if we select a sufficient number of neurons in the neural network, you can always able to find a model which can fit the training output data with a desired accuracy. That's why these neural network models are also called as generalized models, which can approximate any patterns in the data. This kind of a structure of a neural network with the one hidden layer are called as shallow neural network. And here we can observe that by increasing the number of neurons in the neural network, the number of folds or bends in the output curve can be increased, thereby making the NN as an arbitrarily smooth function. This indicates that NN with a sufficient number of neurons can approximate any continuous function with a desired degree of accuracy. And the theoretical results supporting this property are known as universal approximation theorems. Universal approximation theorems or UATs are the theoretical results that will support the approximation capabilities of neural networks. And in the literature, there are two directions of UATs are popular, which are the arbitrary width direction and the arbitrary depth direction. Here is arbitrary width direction focuses on neural network with one hidden layer with an arbitrary number of neurons. And this arbitrary depth direction focuses on neural network with a bounded number of neurons per layer, but an arbitrary number of hidden layers. Here we will be discussing one of the initial theorems in the category of UATs, which is in the arbitrary width direction. And it states that for any continuous nonlinear function, there is a neural network with one hidden layer and arbitrary number of neurons, such that the error between this nonlinear function and the neural network can be approximated by an arbitrary small value epsilon. This basically says that there exists a shallow neural network which can approximate any continuous real-valued nonlinear function in a bounded domain to any desired accuracy. Later on, there were many other versions of UATs were proposed for both shallow and deep neural network. Those supports the approximation capabilities of NNs. So far, we have considered feed-forward neural network, which can approximate the static relationships or static input-output relationships. And here by static, we means the predicted output at the current instant will depends only on the input at current instant. Next, we move on to the recurrent neural network or RNN, which can be considered as a dynamic model or a dynamic version of neural network. And here by dynamic model, we means the current output will depends on the past output and input values. Therefore, this RNN will capture the time-dependent relationships in the data. The RNN we consider in this lecture is an input-output dynamic model and can be used to approximate nonlinear systems as in equation number 12, where yk is the current output, yk plus 1 is the next output, uk is the current input, and f is the nonlinear function which represents the system dynamics. In the RNN, we approximate the model function f using a neural network denoted by fnn, where yk hat is the predicted output, which is an approximation to the output yk, and fnn can be considered as an approximation to the function f. Here theta f contains all the parameters in the RNN, which consist of the weights and biases of all the layers in RNN. The RNN in this equation can be schematically represented as in figure 7, where fnn takes the current input uk and current output yk hat to predict the next output yk plus 1 hat. And there is a feedback connection with a unit delay which gives yk hat, and this recurrent connection or feedback connection makes the RNN a dynamic network. Here by dynamic network, we means that the output at the current instant will depends on the past input and output information. This is one of the initial versions of RNN and can be considered as the simplest form of RNNs. This particular structure is also known in the literature as Hopfield network, and there are many other versions of RNN currently used. In this lecture, we only uses this particular structure, and this structure is useful for implementing output-based NMPC schemes. In the next lecture, we discuss state-based formulation of RNN, which is also called a state-space neural network or SSNN. The SSNN contains feedback connections from some intermediate layers that represents hidden states. Therefore, the SSNN can be used for approximating state-space model, and it is useful for implementing both output-based and state-based NMPC schemes. Similar to the NNN models, we can also represent RNN models as a composite function as in equation 14, where this F1, F2 till FL are the layers of the RNN, and this F1 will takes the current output prediction yk hat and input uk, and the output of this final layer will be the output of Fn. And each of this layer can be represented as a composition of the affine function and the activation function, where Vi is the input to the layer and AFI and BFI are the weight and biases of this ith layer, and sigma Fi contains all the activation functions. Now we move on to the training problem for RNN. in which the available information consists of the input and output data or the training data, which can be represented as in equation 16. Here this capital UD contains all the input samples as its columns, and this capital YD contains all the output samples, and here we consider capital D number of samples are available. Now using this input data and the RNN model, we can compute the predicted output sequence for RNN as in equation 17, where we recursively applying this RNN equation with the initial condition to compute all the future outputs. We have y2 hat is equal to fnn of y1 and u1, and y3 hat will be equal to fnn of y2 hat and u2, and so on. And this prediction basically depends on the weights and biases in the fnn function. Therefore, this can be compactly represented as a nonlinear function fyp, which is depending on this parameter theta f, where theta f contains all the weights and biases in the RNN model. Then in the case of RNN, we can define the prediction error as in equation 18, where Ly RNN denotes the loss function for RNN, which consists of the sum of squared error from k equal to 1 to capital D. And this can be compactly represented as the Frobenius norm of output data YD minus its prediction squared. And this we can also expand it as trace of YD minus YD hat transpose YD minus YD hat. And for YD hat, we use this expression. This means that this prediction error will be a function of the model parameters theta f, and the resulting RNN training problem can be represented as an equation 19, where the objective is to find the optimal parameters theta f, which minimizes this loss function. As we have seen in the case of neural network with the ReLU example, once we fix a particular activation function, the output of the neural network will entirely depending on the weights and biases in the model. And here also it will be true. Once we select a particular activation function, the output of the RNN will be entirely depending on the weights and biases in all the layers. Therefore, here our objective is to find the optimal values of these weights and biases so that the output of the RNN will closely matches with this training output. And once the optimal parameters are computed, we can define an RNN using the corresponding weights and biases and use that RNN for prediction. Now, similar to the NN, we can also have a universal approximation theorems for RNN as well. And here we have assumed that the nonlinear function which generates the training data is a Lipschitz function. And here by Lipschitz, we means that there exists a constant LF such that the difference of this function between two different output can be bounded by LF times the norm of this y1 minus y2. Under this assumption, for any epsilon greater than 0, we can always find an RNN such that the output prediction error or any finite number of samples is bounded by epsilon. This indicates that if the actual system which generates the data is Lipschitz, then we can always find an RNN which can approximate the actual system dynamics in such a way that the prediction error can be bounded to an arbitrary degree of accuracy. Next, we move on to the RNN-based data-driven NMPC, in which we will be using the RNN model for implementing an output-based MPC scheme. Here we compute the control reference UR by using the steady-state condition for outputs, where we replace the yk plus 1 and yk hat in the RNN equation with the YR, which gives the equation 23. And using this YR and UR, we can define the optimization problem for RNN-based NMPC as in equation 24, where we consider output-based NMPC problem as discussed in the previous lecture. And here this FYP function will be constructed using the RNN model, which is identified from the training data. Algorithm 1 summarizes the steps for RNN-based data-driven NMPC, in which we will be using the training data UD and YD to find the optimal parameters for the RNN, which is denoted by theta f star. Then we select the parameters for the NMPC, and during each time instant, we solve the optimization problem to find the optimal value of the control input UK star. And the first element of the control input will be applied to the system at each time instant. Next, we illustrate the RNN-based data-driven NMPC using a numerical example, in which we consider a second-order nonlinear system, which is called as continuous stirred tank reactor or CSTR system, and it can be represented in discrete time as in equation 25. We will be using the system parameters for the system as in equation 26, And this system is simulated for 500 instances to generate the training data for the RNN. Then using the training input output data, we identify the optimal parameters for the RNN model. And then in the MPC, we select the prediction horizon as 10 and the simulation horizon as 200. And the other parameters as shown here. Figure 8 shows the response for RNN-based data-driven NMPC, in which this subplot A shows the training input and output. And here the training output is shown in red color and the predicted output is shown in green color, where we can see that the prediction is matches with the actual output. Figure B shows the response of the data-driven NMPC with the RNN model, where we have the reference value in green color and the output in red color. And it can be observed that the output is able to track the reference. Figure C shows the control input with the MPC scheme. And here we can observe that the control input is satisfying the constraints. The MATLAB code for this numerical example can be downloaded from the link given in the description. In the next lecture, we will be discussing state space neural network, which is a popular version of RNN currently used, and we discuss its application in NMPC. That leads us to the end of this lecture. Thanks for watching.